Hi guys, today we are going to discuss about mixed strategy games in non-cooperative games. I am Dr. Ganesh. Welcome to this course. So let's recap. What is a game? What constitutes a game? Do you remember? Yeah, so primarily players who are the decision makers. The actions, what players can do, and the strategies, which action did I choose, and payoffs, what motivates me to choose that particular action, and outcome, what is the result. So to recap the concepts quickly, we learned about two-player games. We spoke about Nash equilibrium, the key way how we find an equilibrium under uncertainty in the presence of lack of coordination, where people do not trust each other, where people care only about their benefits. Nash equilibrium is prevalent. We also spoke about one way of finding Nash equilibrium, which is through the concepts of dominated strategy and dominant strategy. We have seen the matrix representation and the normal form representation of a game, and that is used to solve and find Nash equilibrium in case of a non-cooperative simultaneous game. Games with no pure Nash equilibrium. Let's take an example. Suppose there is a football, a soccer, and a penalty is happening. The Either the goalie or the penalty taker will win, not both of them, right? So that is an example of a game with no pure strategy Nash equilibrium. You can see in that matrix, if you work out, none of the column or row will be, none of the cell will be a final say this is the best equilibrium strategy which is good for both of. Let's take another example, old classic economics or business example called the compact disc battle. So there was a battle for competing technical standards where Sony and Philips, who were the leaders of compact disc, were competing for a standard in late 1970s. Each wanted their own system. So you see a sample matrix. If Sony and Philips both use a standard A, standardization gives them some good benefit. So 5,4 and Y5 for Sony is because Sony is extra happy because it is their standard that came into effective. Now what about standard A and B? Since each one is using their own standard, Sony uses standard A, Philips uses standard B, that leads to 1,1. Now what about Ulta, reverse? That means Sony uses Philips standard and Philips uses Sony standard. This is very unlikely to happen. If that happens, we assume no benefit. And finally standard B, used by both, which was invented by Philips, so Philips is little more happier. And standardization happened, so that is 4 for Sony. So if you see here, there are two equilibrium, standard A, and standard B. So what will happen? A mix of both standards resulted in the end of this game. Another very classic example of game theory. I remember we have seen Prisoner's Dilemma. So another one is Battle of Sexes. At their separate workplaces, Ram and Sita must choose to attend either cricket or a movie in the evening. Both Ram and Sita know the following. Both would like to spend the evening together, but Ram prefers the cricket and Sita prefers the movie. One way of putting the matrix together is this way. Numbers are representational. So since RAM prefers cricket, and if they both go for cricket, RAM is higher, RAM is happier, and the fact that they are together is okay for Sita, and vice versa for movie, comma movie. In either of the other two cases, they are not happy because irrespective of what they individually like, they ultimately wanted them to spend the evening together. So cricket, comma movie, or movie, comma cricket gives them 0, 0. So in this example, there are two strategies. So there are two pure strategy equilibria, Nash equilibria, which is cricket, comma cricket, and movie, comma movie. So the concept of mixed strategy comes here. Since there is no single pure strategy equilibrium, we have to potentially use the concept of mixed strategy equilibrium. So a mixed strategy of a player is a probability distribution over players' pure strategies. So assume P and 1 minus P are the probabilities with which Ram will choose cricket and movie. So P is 1 when Ram actually plays cricket. P is 0 when Ram actually watches movie. But the probability distribution is P is the probability of playing cricket and 1 minus P the probability of watching a movie. And then the mixed strategy will be found as a function of the probability distribution by both players. Let's take another example and solve it completely. I strongly recommend after solving this you go back and try solving Battle of Success game also. So there is a famous game called matching pennies. There are two players, each one has one penny in their hand. They should simultaneously choose whether to show head or tail. They know the rules. If both pennies match, either both heads or both tail, player 2 wins player 1's penny. Otherwise, player 1 wins player 2's penny. Can you draw the matrix? Pause the video, draw the matrix, and see how it looks like. Okay, so did you get something like this? If both are head, player 2 wins, so player 2 gets 1 from player 1 and player 1 loses 1, minus 1. So this is essentially a zero-sum game also, right? Can you observe that? Okay. Now this is very similar to our soccer example that we discussed earlier in this video. There is no pure strategy equilibrium. So the way of finding a mixed strategy equilibrium is through the probability distribution. So let's assume Q is a probability with which player 2 plays head, and 1 minus Q is a probability with which player 2 plays tail. R is a probability with which player 1 plays head, and 1 minus R is a probability with which player 1 plays tail. What is player 1's expected payoff? So expected payoff means in the absence of a pure equilibrium, what do we expect? A probabilistic output of what can I expect out of this game? The expectation may not be reality because there is a probability distribution involved. So if player 1 chooses head, he will get minus 1 with a probability Q because that is the probability with which player 2 will choose head. So minus 1 times Q plus 1 times the probability with which player 2 will choose tail, which is 1 minus Q. So minus Q plus 1 minus Q, which is 1 minus 2Q. Similarly, if player 1 chooses tail, his expected payoff is Q times 1 plus 1 minus Q times minus 1. Now I suppose you understood how we use Q and 1 minus Q for player 1 because I am calculating the utility and the chance that I am in that particular cell plus utility and the chance that I am in the second cell, so on and so forth. So we got these two values. Now we know naturally when both of them are equal, the player will be indifferent in choosing both strategies. So by equating them and solving, we will get q as 0.5. So at 0.5, player 2 is indifferent between head or tail. Now when q is greater than 0.5, we can observe 2q minus 1 is greater. So player 2 will choose tail. For q less than 0.5, 1 minus q 2q is greater. So player 1 will choose head. So it says if you think the probability distribution of player 2 is that with the probability half he will choose. Whenever that probability is less than half, choose tail. Head, greater than half, choose tail. Can you do a similar analysis so we can also plot this on a graph. This is how it looks like. Can you pause the video, calculate the same thing for player 2. As a function of R, can you determine the best response for player 2? Calculate expected payoff, best response, and then plot it on a graph. Okay. So you can similarly calculate the value. Player 2, if he choose head, it will be 1 times R plus minus 1 times 1 minus R. So 2R minus 1. And tail is minus 1 times R plus 1 times 1 minus R, which is 1 minus 2R. So that is expected payoff. From that we can again equate them, find out the indifferent value. Then for greater and lesser values we can find out which is doing better. We will understand something similar. Now I am plotting this on the same graph. That graph is a function of R, Q and R. So if I plot it, I will get it something like this. The indifferent value. Now let's superimpose both of these, the P and Q. Wherever they meet is actually going to be the mixed strategy equilibrium. So the point where they meet is half comma half, which means P equal to half and Q equal to half and R equal to half is the mixed strategy equilibrium in this particular game. Suggest you to pause the video here, understand it, and then proceed. So what is the definition of a mixed strategy? We have already defined it. A mixed strategy of a player is a probability or distribution over players' pure strategies. So sum of the probability should be 1 and probability should be an element in strategy sets. Each probability leads to one of the strategies. Player 1 has two pure strategies H and T, and mixed strategy is any of the probability distributions. Choosing head and tail with half-half is a mixed strategy. Choosing head with a probability 0.3 and tail with a probability 0.7 is another mixed strategy. So there are infinitely possible mixed strategies, and we found that 0.5 is the mixed strategy Nash equilibrium. There is another game. Row chooses top with the probability P and bottom with probability 1 minus P. Column chooses left with the probability Q and right with the probability 1 minus Q. You can determine the steps are exactly similar to the previous game. You work out and then verify that your answer is 0.25 and 0.5. Mixed strategy Nash equilibrium does not rely on a player flipping coins, rolling dice, or otherwise choosing a strategy at random. Another example, can you calculate the mixed strategy equilibrium of rock, paper, scissor game, which we have discussed in the one of the previous videos? And I strongly recommend this is also the right time to go and find out the mixed strategy equilibrium of Battle of Sexes game. Let's take a real application from computer networks on how non-cooperative games, simultaneous games are used. This is called forwarder's dilemma. There are two cells, blue and green. Blue needs to forward a packet, send a packet to blue tower, but it needs green's help to forward it because of the distance. And green has a packet to send to green tower and it needs blue's help to forward it. So if you forwarding has an energy of cost C, which is a very small value, successfully delivered packet. So if blue's packet gets delivered, blue gets 1. If green packets gets delivered, green gets 1. If green drops and blue forwards, what will happen? Blue forward means green's packet will reach destination, so green will get 1. And blue's packet did not reach destination, but blue forwarded, so there is a cost involved, so minus C. If green forwards and blue drops, reverse. If both forward, it is 1 minus C, 1 minus C. How did you get? The 1 for green is because blue forwarded green's packet, and minus C is because green forwarded blue's packet, and you have to interpret it that way. If both drop, no cost involved, no packet reach the destination. Each player is trying to selfishly maximize its next gain. Assume they are rational, lack of trust, no third person to coordinate activities. By the way, this example is taken from Buttayan and Hubax on security and cooperation in wireless networks. That is a material I referred. So can you pause the video, draw a matrix, and then determine the equilibrium? So what will be the Nash equilibrium? Naturally, let's take it the way we typically find Nash equilibrium. If green forwards, what is the best strategy for blue? If blue forward, he will lose some energy. If he drop, he will just gain something. So the best strategy is drop. If green drops, then blue will either incur a cost of minus C or nothing happens. And nothing happens is better than losing energy, so drop. Similar analysis for blue being a symmetry game. So this quickly leads to Nash equilibrium being drop, drop. So in the absence of any other incentives or coordination, rational players will not participate in the game. So even though the optimal answer could have been 1 minus C, 1 minus C by helping each other, but without a coordination or incentive, nobody is going to do that. So the Nash equilibrium is 0, 0. So the equilibrium concepts, what we have seen is plotted in the green color, highlighted in the green color. When the information is complete and the game is static, that means simultaneous game, the Nash equilibrium concept is generic. There is already a video on incomplete Bayesian concept for static games, so please do refer that. In the upcoming video, I will be discussing about dynamic games of complete information, where we use a concept of subgame perfection. And you can refer to my material on Bayesian games to get some idea on dynamic games of incomplete information. But I would strongly recommend that my next video on dynamic games of complete information must be listened before you listen incomplete dynamic games, which will be modeled using Bayesian modeling. Summary, we learned simultaneous games. So the next video we will discuss about sequential dynamic games of complete information. And with that, let me thank you. Bye.